This is a three-phase synchronous brushless DC motor.
And it's just as complicated as its name suggests.
Three-phase brushless DC motors, or BLDC motors for short, are much more accurate, powerful, and efficient than normal DC motors, so they have many uses, including
electric cars,
Quadcopters,
computer hard drives,
robots,
electric bikes,
and even air conditioning.
In order to see the monumental progress of the BLDC motor, we first must look at the previous iterations of electric motors throughout the years. First came brush DC motors, which used carbon brushes that move inside the motor. This is very inefficient and creates waste. BLDC motors were invented in the 1960s, but were not able to generate much power at that time. In the 1980s, however, Robert E. Lordo, using the newly invented microcontroller to precisely control current, generated much more power and speed and allowed for the spread of BLDC motors into everyday items. But how are they made?
How do you control them?
and how do they work?
Let's
find out. In a BLDC motor, there are two main parts, the stator and the rotor. In the stator, which stays in place, there are three coils, each with an iron core that propagates the coil's magnetic fields, which are induced as current runs through them. The rotor spins around the stator and usually has one more permanent magnet than coils on the stator, with alternating polarity as shown. The three coils are connected at a neutral point in the middle, which allows 6 different paths of current between the coils. By quickly alternating between the 6 steps, the rotor will rapidly change its alignment, causing the motor to spin. Most BLDC motors contain more than 3 coils, always in multiples of 3. The extra coils are connected in series so that there are always 3 sets. The greater amount of coils allows the motor to spin more accurately. BLDC motors can spin very fast, so to control them and rapidly change the current through the coils, external electronic components are required.
The motor is driven using a series of switches called MOSFETs. MOSFETs are semiconductors that require little to no power to be controlled, but can control very large loads. A MOSFET has 3 terminals: drain, gate, and source. In an N-channel MOSFET, the drain is where current enters the MOSFET, and the source is where current leaves. In order to turn the MOSFET on and off, a voltage must be applied to the gate. Every MOSFET has a threshold value dictating how much the gate's voltage must exceed the source. If the threshold voltage is achieved, the MOSFET turns on. If not, the MOSFET turns off. Here is an example circuit. A pull-down resistor is placed on the gate to ground in order to bring the gate's voltage back to ground once the switch is released. Notice that the MOSFET connects the load to ground, allowing or disallowing current to flow. This is called a low-side driver. N-channel MOSFETs are typically used in this configuration. Let's try putting the MOSFET on the high side of the load. If we turned on the MOSFET, current would begin to flow. As current begins to flow through our load, the voltage drop across the load would rise. As this rises, the voltage of the source of the MOSFET would begin to rise as well. But the gate voltage, however, would not. This means that at some point, the voltage between the gate and source will soon drop below the threshold and turn the MOSFET off. Then the cycle will repeat. Enter bootstrapping. Bootstrapping is a method for using an N-channel MOSFET as a high-side driver. To do this, you place a capacitor between gate and source like so. When the MOSFET is off, the capacitor charges to have a voltage potential of VDD. When the gate is released from ground, the bottom of the capacitor rises almost all the way up to VDD. Since the top of the capacitor is connected to the gate to source voltage will be equal to the voltage potential of the capacitor, which is above the threshold voltage of the MOSFET. Now that we know how to use a MOSFET as a high and low side driver, we can create a half bridge, most commonly known as an H-bridge. An H-bridge allows for one side of the load to be pulled high or low. Now that we have one H-bridge, we can use 3 H-bridges, one for each phase, to control the direction of current in each phase. But all these electronics would be blank slabs of silicon without the help of some software.
The circuitry while rightfully complex, does not work alone. In order for the right amount of current to flow in the right places, a microcontroller is needed. The microcontroller is controlled by programming written to tell the circuit board when, how much, and where to put the power from the power supply, turning on and off the MOSFETs in the correct order that we saw earlier. That order, controlled by the aforementioned MOSFETs, is 6 steps long. The first step is triggered by switching on one of the MOSFETs on the high side, so that the high side connection is made through phase A to the neutral point, and then a low side MOSFET is switched on so the neutral point is connected through phase C to the low side connecting wire, which pulls the circuit to ground. In this way, the motor has made a connection from a power supply to ground through a coil, which produces current within the coils, generating a magnetic field. The magnetic field generated as current runs from the power supply through phase A is directed in towards the center of the motor and the neutral point. This magnetic field aligns with that of the permanent magnetic field of the northern pole of the rotor magnet, attracting the northern pole and repelling the southern pole. The opposite is true for phase C, where the current flows from the neutral point towards ground through phase C, generating a magnetic field that phases outward towards the rotor, aligning with the southern pole of the rotor's magnets and attracting the southern pole and repelling the northern pole. This pattern repeats as the motor runs through the 6 steps, which repeats as following. First, phase A to phase C, as we just saw. Then, phase B to phase C. Next, phase B to phase A, followed by phase C to phase A, after which is phase C to phase B, and finally, phase A to phase B.
So, to wrap up this riveting discussion of BLDC motors, we want to reiterate some final points. First, BLDC motors are efficient, accurate, and versatile, and they have 2 main parts, the rotor and the stator. The rotor has magnets and spins around the stator, which has coils, and thanks to the microcontroller and some clever MOSFET configurations, the ESC can pass current through the 3 phases of coils in a way that makes the rotor's magnets become attracted and repelled in order to rotate the 360 degrees. So, all in all, for all of your precision and rotational needs, the BLDC motor is the way to go. Thank you for listening.